So, the drill about like do before the unit test, et cetera, et cetera. Let me open the file. You see a data set, very not so complicated data set, but it's still a data set. What we're going to do with that looks very complicated, although it's really not that bad. All right, I'm going to talk you through it first, and then I'll go through the example with you. All right, so you have this data set. We're going to plot the data set. We're going to plot the points. These are some of the common types of regressions that you can get. We're going to focus only on polynomial regressions because that's kind of where we've been living in this course up until this point. We've done stuff with logarithms, but we're not really focused on that just yet. We're not experts on logarithmic graphs just yet, but we're a little bit more attuned to the concept of polynomial functions, so we'll stay there. All right. So we're going to find the polynomial regression model that best fits the data. All right. The best fit model is the one that has an R² value closest to 1. All right. That doesn't mean a whole heck of a lot right now until you see it in action in Desmos. But once you do, you'll see what I'm talking about. All right. Then once we have that information, we evaluate our function for when x is equal to 1. Then we find the time when the temperature is at a minimum, and then we find the time when the temperature is at a maximum. So these are what we call extreme values. Sets you up nicely for some concepts in calculus. All right. So I'm going to open my Desmos, and the assignment has a fresh set of data that you'll pretty much do the same thing with. All right. So your assignment will be a data set that I give you, and then a data set that you yourself collect. However, a lot of you did the bonus assignment in Unit 1. That was my way of tricking you into collecting data. All right. So if you did the bonus assignment in Unit 1, you already have a data set. All right. So you can actually just use that for this assignment. All right. That was kind of like my thinking going into it. All right. It was sort of mean in the sense that I knew you were going to have to collect the data anyway, but some of you got bonus, some of you didn't. That's the price or the reward for being industrious. Anyway, so I'm going to open a Desmos stack cam. I'm going to open a graphing calculator. All right, I'm going to hit that little plus sign. A little plus sign that says add item. I'm going to click on that. There's an option for a table. I'm going to click on that. And I'm going to start typing in all these values. All right. I didn't put too crazy of a data set, and there was a reason for that. I didn't want it to be too overwhelming, but it is still kind of annoying that you kind of sort of flip back and forth between the two. I'm kind of going the lazy approach here and taking a picture of the data set, and then I'll just refer to that as I go. But just whatever it takes to efficiently get the data in. Right. So from 0 to 14 by 2, so 0, 2, and you see it auto populates, which is kind of nice. I mean, it's more than kind of nice. It's wonderful. Right. So once you see that it's auto populating, you can start just hitting enter, knowing that it's going to follow the trend. Right. So that's good news. Can't always count on that because sometimes the numbers aren't as friendly, but in this case they are. Right. So we have 94. We got 82.9. We got about 4. Geez, I already had the 4, crying out loud. All right. What I meant to say was 73.6, 65.7, 49, 53.3, 48.5, and 44.4. All right, so there's my raw data typed in. Not too bad. All right, so what we're going to do is we're going to try some of these functions. It's a fair amount of typing, and that part is definitely on the tedious side, but it's one of those things where if you do it right the first time, then you could use this same Desmos over and over again for any kind of regression. All right. So what we do is we type in y sub 1, right? And in order to type in a y with a subscript of 1, you just type in y and then the number 1 after it. I don't know why Desmos knows that that's a subscript, but it does, and I'm happy it does. All right. Then you type in a tilde, which I almost always forget to do, and I end up scratching my head over why things aren't working. But y sub 1 tilde a plus b x1. When you type that in, what it does is it presents you with a printout, a little display, one of which is an R squared value. Now, it's a statistical concept, so you really have to kind of delve into the world of statistics. I mean, really, more than just this introductory statistics class, in order to understand that there is a difference in computation behind lowercase r squared and capital R squared. But in terms of determining the relationship, they actually mean the same thing, right? For our purposes, it just means if we see a lowercase r squared or an uppercase r squared, we treat them the same way, right? We're looking for a value that's close to 1, right? This is pretty close to 1, 0.9154. I want to see if there's a better option, though. Also, you may have noticed that as we typed all this stuff in, nothing has appeared on the screen, right? And there's a good reason for that. If you look at the y values here, you see that they're way bigger than 8. And that's the highest y value I have displayed on my screen, right? The biggest one in my y1 column is 94. So I want this thing to go up as high as 94 at least, right? So what I can do, instead of just kind of zooming in and out and hoping for the best, I can hit that little wrench, the little wrench icon, graph settings, and just change my y-axis high value. You got your lower bound and your upper bound. Change the high bound to something bigger than 94. I'll make it 100. And now you can see there's a lot of fun stuff here. You got all the points, right? The 0, 94, and so on. And you also have this line that represents what we call a linear regression model, also known as a line of best fit, right? All of these are what we call curves of best fit. They're curves that, you guessed it, best fit the data set, all right, depending on the type of model that we select, right? So that's a linear model. It's good, but is it the best? We won't know until we investigate further. So we investigate further. So my next possible candidate would be the quadratic case. So I type in y1 tilde a x sub 1 squared. All right, if you're looking for a power of 2 on the keyboard, I mean, I do this all the time, but I don't think I ever mentioned it. Just hit Shift 6. That's the caret symbol. It's the keystroke to get you a power, right? But then hit the right arrow to get out of the power, plus bx1 plus c, right? That's the general form of a quadratic. And you can see that the r squared now is capital. That's fine. We treat the lowercase and the uppercase r's the same, right? But this r squared is closer to 1 than this one, right? So what I would do is I would turn this one off, right? I don't want to look at this one, right? This actually looks like it's a better fit for the data, but now I'm getting greedy. I want to see if there's an even better option out there. So I'm going to look for a cubic, right? So y1 tilde ax1 cubed plus bx1 squared plus cx1 plus d. All right. Better, but not by much. All right. Only a smidge better. All right. And in fact, they would round to the same answer. So if I had to make a choice between the quadratic and the cubic, I would actually go with the quadratic because we're looking at a simpler function and the difference between the r squared values would be negligible, right? But we're going to also investigate the quartic and the quintic. So technically the cubic is better, so I turn off the quadratic, all right? So now y1 tilde ax1 to the fourth power plus bx1 to the third power plus cx1 to the second power plus dx1 to the first power. But then I'm going to skip, and this might be a little aggravating. I'm going to skip E and I'm going to skip F, and I'm going to go right to G. All right, there's a good reason for that. And I'll actually just show you why we wouldn't use E. If you look, I type in E, and you look at my little printout here, I don't see an E. All right, type in F. Well, it actually gave me an F, but it doesn't always, and I'll explain why in a second. All right, G, it gives me a G value. Whatever I put in as a coefficient, it needs to be displayed down here under the parameters. So you'll see that the E doesn't get displayed. And the reason why is E is an actual number. All right. So E, if I type in E into Desmos, it's an actual number, 2.718. It's Euler's number. All right. We stay away from F because very often we define a function as F of X. All right. So we very often use F for something else. So we don't want to use F here. Right. So we always skip E and F and go right to G. Right, as annoying as that might seem. All right, but then you could carry on after that without restriction. Now, looking at this, is it better? Yeah, a little bit. 0.976 as opposed to 0.97. This would round to 1. So this so far is my winner. So then I would go to the quintic, a fifth degree polynomial. And you could actually keep going after this, but typically we stop at the quintic because you don't, the amount of accuracy you gain beyond the fifth degree polynomial is negligible. So ax1 raised to the fifth plus bx1 raised to the fourth plus cx1 raised to the third plus dx1 raised to the second plus skip E, skip F, G, X1 plus H. All right, and so now we're up to 0.98. All right, our R squared value is better now than it's been all along. And you can see it's a pretty good fit. Now, we don't know if this is actually a good contextual model. We don't know if the context of the situation is going to suggest that this is actually the best function to use. I can tell you right now that when you're dealing with cooling and warming, temperature changes and things like that, it's actually better suited for exponential functions and logarithms. But we're learning about polynomials right now, so we kind of limit it to that. All right. So what we're going to do is evaluate this function because everything else is the loser function. All right. We would say, all right, well, this is my winner. So this is the one I want to have as my function. All right. So all of these coefficients would get plugged in and we would rewrite our function as a new function that we would call f of x using these parameters. All right. So what I would do, because there's a bunch of different ways to do this, and I got to say there's actually a more convenient way to do it, but it involves you deleting all of this other stuff. And I actually need to see all this other stuff for you to get credit. So I'm going to show you the way that you're probably not going to love, but this is the way we're going to do it. All right, we're going to rewrite this function as f of x is equal to, we're going to put in our a coefficient. All right, so our a coefficient, x squared, just an ordinary x now. Our b coefficient, x to, I think I said x to the x squared, I meant x to the fifth. Our b coefficient, x to the fourth, our c coefficient, x to the third, and so on. We're just going to type that in, right? So negative 0.00151,843. That would be x to the fifth, right? So now we're going with regular equal signs, regular x's, none of this x1 business, no tildes, nothing like that, right? So plus 0.0479485 x to the, I got to fix that. Sorry, I wrote x to the third, I meant x to the fifth. Let me just go back. So then minus 0.496995. I'm just putting the whole decimal in. X to the third plus 2.03127 x squared. A little easier to type as you go. There's less stuff to type in, you know. Understatement of the year, I guess. X, and then plus 93.9124. And this is where you find out whether or not you typed it incorrectly, because this should match up, the red should match up with the black. Turn them off and on and make sure that they do. So we're in good shape there. So now what we do is we just live off of this red function, right? Because we can manipulate this. So in the next part of the assignment, it says, use the best fit model, which we just figured it out. I'm sorry, using the best fit model, evaluate the function at x equals 1. Very easy to do now, because all I have to do is type in f of 1. All right. Now, I didn't ask for any kind of interpretation, but since, I might as well talk about it, since x represents the amount of time that's passed or elapsed, time in minutes, and the y value represents the temperature, what this is telling me is, following this model, this item that was taken out of the oven would have an internal temperature of about 88 degrees after 1 minute. All right. Now, it also asks us to find the time when the temperature is at a minimum, and the time and when the temperature time at which the temperature is at a maximum. All right. So we're looking at this function. Now you could zoom in, zoom out. It looks like it's infinite if you go forever to the left and forever to the right. So we're not really concerned with those. So we would just focus in this neighborhood. We're not concerned with negative time, right? So we would only care about this function once the clock starts, so only at this location here, right? So if I'm looking at this graph, it's asking for the time at which the temperature is at a minimum and a maximum. So I'll answer it in the order that they asked. I already forgot those. Let me look, right? So we're looking for the minimum first. Just following this, well, I mean, it's infinite, and really temperature can have a set of negative values. So on the low end, I mean, you could say 0. I mean, these are degrees Celsius. I would think a safe bet would be 0, because 0 degrees Celsius would be freezing temperature. So it's at a minimum at this moment here. All right. So we could say minimum temperature. So if you want to put in a statement, you want to write a note in Desmos, you open quotes, and then you could just type ordinarily, right? Or you can hit that little plus sign and put in note, and it'll say enter a note. Either way. But I would say the time that the object is at a minimum temperature would be 16.086 minutes. right? And then for the maximum temperature, again, because we don't care about what happened before the clock started, we don't care about any of this. The maximum temperature would be the moment it was taken out of the oven, right? That would be 0.94. Or if you're going by the function itself, the function tells you something slightly different, but they do round to the same value, right? So the time at which the temperature would be at, I'm going macro rules here, hold on, Control C, not Command C. At a maximum temperature would be 0 minutes. All right, because again, it's just saying find the time when the temperature is at a maximum, the time when it's at a minimum. It's not asking what the maximum temperature or minimum temperatures are, right? The times at which you would be at those temperatures, right? And so that's all you'd have to do for a question like this. Your assignment is to basically do the same thing, just using this information, right? Context changes, it's time and distance instead of time and temperature, but you find the best regression model. And if you really think about it, all you would have to do, and that's the benefit of doing this example along with me, is all you'd have to do is overwrite the data in this table, because everything that we did after that is based off of the values in the table. All right. So if I take the data that was given here and put all these values in my X1 column and all these values in my Y1 column, then everything beyond that will change accordingly. You might have to change the window in order to see the points, but all of these values will change accordingly. Like, I'll just show you really quickly. If I change this 14 to a 140, just take a look at this R squared value right here. I'm going to change that 14 to a 140. All right. It went from 0.9 something to 0.2 something, right? By changing entries in the table, you change the outcomes over here in the printouts, right? So then everything beyond that, I mean, you'd have to change this. This should stay the same because it's asking the same question. What's the distance traveled after 1 second, right? And then maximum, right? The little add-on there is to explain what it means in the context of the situation, but that shouldn't be too bad if you dive into the data, right? And then the follow-on, the second part to your assignment is to just do all that again with your own data rather than the data that I give you. Makes it a little bit more authentic. All right.